In this short video, I will show you how to use the jitter analysis and real-time eye features on Agilent's Infinivision 6000X series oscilloscope. Let's get started. You can see here on the screen that there's jitter on the clock edge. You can tell because the edge appears to be bouncing around relative to the trigger point. This is referred to as time interval error, which means that the edge is either occurring too early or too late in relation to the sample point. This can cause sampling errors at the receiver of your device. Many times with high-speed serial buses, the clock may not be explicit, which means that it must be recovered at the receiver. We can use an oscilloscope to simulate the receiver by using its clock recovery algorithm. Sometimes jitter may not be as obvious, and so it's important to use jitter analysis to uncover it. Let's use the 6000X series jitter analysis to try and find the cause of this jitter. We will first need to enable the jitter analysis and add a time interval error measurement that will be based on a constant clock recovery. This will simulate a receiver with no filter. The auto setup keys make it easy to enable various jitter measurements, and each plot will be based on timing errors of each edge of the signal relative to the recovered clock. First, we will enable the histogram. The bimodal distribution reveals deterministic jitter is affecting the signal. Now let's enable the jitter trend waveform. The purple waveform is time correlated to the captured signal. Notice that the jitter trend has a sinusoidal modulation, which indicates that periodic jitter is affecting the signal. We can use the built-in measurements to determine the frequency of the trend line. Using the 6000X series jitter analysis feature revealed that the jitter was periodic and had a frequency of about 100 kHz. The real-time eye feature is another way to view the effects that the jitter has on the signal. We will first acquire the real-time eye with a constant clock recovery, which will simulate a receiver with no filter. Under the Analyze menu, select Features, select Real-Time Eye, and we can make sure that the clock recovery is set to constant frequency. Now press Acquire Real-Time Eye. An eye diagram is an overlay of individual bits based on the clock recovery. You can see here that the eye is closed, which is due to the edge shifts of each bit. We can also draw a box at the signal 0 crossing and enable the histogram to visualize the jitter distribution within the box. An ideal eye diagram would be open, showing that there isn't any significant jitter affecting the signal. Another type of clock recovery used in high-speed serial buses is a phase lock loop bandwidth filter, which can help to eliminate jitter. First and second order phase lock loop clock recovery can be used to simulate this on the 6000X series oscilloscope. Let's change the clock recovery to a PLL to try and filter out this jitter. This particular signal has a speed of 10 megabits per second. And from our first measurement, we determined the frequency of the jitter was about 100 kHz. We could set the bandwidth loop to 1.5 MHz to ensure we have filtered out the sinusoidal jitter and all of its higher harmonics. Now we will acquire the real-time eye again. As you can see, the eye has opened and is not being affected by the jitter anymore. The histogram has a Gaussian distribution, which also tells us that we have successfully filtered out the jitter. In this short video, we use the oscilloscope to simulate a receiver on a high-speed serial bus. For more information on the Agilent Infinivision 6000X series oscilloscope, please visit agilent.com. And for a live demonstration, please contact your local Agilent representative. Thank you.